Hey, Soleil.
Hey, hey.
So let's dive right in.
All right.
Can't see you, by the way.
Oh, always starts with no camera. Here we go. I'm here. Woo! You can see me now.
Yep.
We left off on a peculiar little ending.
A what little ending?
Ending of I
No,
grasp. I grasp, but I don't
oh, I want to
grasp.
know. I want to know the word you used.
Peculiar, like it's
Peculiar.
interesting.
Yeah.
Like a interesting ending to
So
X.
let's walk through it again.
Yeah.
We have a line. We cut the line at some strange place. Um, if we
Strange
say that
face.
this is one and this is X, we'll use X today, or A.
Right.
If this is one and this is A, then A divided by 1, the small to the big, small to the medium, is equal to the medium to the big.
Yep.
So if you can come up with that equation, that's great. Then we saw that that's the same as this. And just take the 1 out the bottom because A over 1 is A.
A divided by 1 plus A is
So this goes to this. All I did was I took this off.
yeah. Right, because I remember yesterday we did something where we solved that last part. It was A over 1 equals A.
Well, let's stay with this right now. So the next thing we did was this. We said if we multiplied both sides by 1 plus A, that 1 divided by 1 plus A and then multiplied by 1 plus A would give us just 1 on this side. And then on this side, we'd end up with A times 1 plus A. Or the other way around, right?
Okay.
Let's take it a step at a time and make sure that you get every single step. I don't need to go faster than you. I think I went faster than you. So how about this? Do you feel good about that?
Yeah, I mean I get it, but I don't know it.
Well, then I would say you don't even get it. There's no intermediary here. Look, the small is to the medium.
That part I get. I can visually,
Is to the bottom.
conceptually understand that, and in my mental mind, the image itself, it makes sense. Like my brain is drawing pictures in my head that make sense. It's the numbers part that I'm
Okay,
struggling.
so what does this mean? What does remember? Okay, so we're going back to fractions. 3/4, right? So the
Right.
top number divided by the bottom number. So what is it's interesting. You're calling it numbers. It's interesting that you're calling it numbers because when I don't even to me I don't see numbers. I see the picture when I look at the equation.
Mm,
And all I see is that the ratio of A to 1 is equivalent to the ratio of 1 to 1 plus A. I'm just seeing equivalent ratios. It's kind of like, the squirrel is to the dog, as the dog is to the bear, as the bear is to the lion, right? They're like going up by the same amount each time.
I
Relative.
don't get that one.
I'm like, it's like, okay, so it's like a small thing. So let's use a different example. 1, twice as big,
Yeah.
twice as big.
Yeah.
So so the relationship between these two is the same as the relationship between these two.
Yes.
This guy looks down, is a guy, and this guy looks up, and he says, "Hey, you're half as tall as me." And then this guy turns around and looks down, cross-eyed. Let's do the cross-eyed.
All good.
No, we want to look down. There you go. He looks down and he sees this guy and he says, "Hey, you're half as tall as me." Relatively speaking, you got to get relativity. It's essential in life and music too, by the way. Relatively speaking, these guys are small to big by a factor of 2, and these guys are small to big by a factor of 2. It's the same factor.
Yeah, this is the part I get. See, when you're doing pictures, no problem.
Okay, so the math describes the picture. So if I call this Q, R, S, I'm trying not to use A and B. Q, R, S, still orders, but you might not associate. Q to R, that is the relationship of 1 to 2.
Okay.
R to S, that is also a relationship of 1 to 2. In fact, those are equal to each other. Q to R equals R to S.
Okay.
Let's do more than an okay.
Yeah.
I want this to be like
Yeah, I get that. Okay, that works. That works. That's clicking. I'm looking at brand new letters, and I mean, I know they're just a different reference point. But it makes sense.
you know, I could use any symbol you like. I could say
Yeah.
Q to R is the same as R to S. I just made up completely random symbols here.
Yeah, this part I'm getting. So it's when I look at the numbers themselves
Okay, so
that
how is this a number?
those aren't numbers.
Well, but they are. You see, everything's a number if you look at it in a certain way. Anything that can be quantified. So let's, this is, so what you're gonna learn here is like a paradigm shift. I want to help you, grasp the world as a mathematician grasps the world, and tap you into your multi-life predilection that you haven't been tapped into yet. Or you have been, but let's like break it through, breaking completely here. Everything is quantifiable. Quantity. Quantity is a number. Quantity is a measurement. Quantifiable means that you can measure it. I'm just saying in a few different ways just to make sure it really sinks in, okay? What can't you measure? Perhaps eternity. And basically, you can't measure nirvana. You can't measure God. Everything else you can measure. And if you want to measure God, you could call it like infinity or 0, right? It's like at the very edges of measurement. Why? Because eternity has no moving parts by definition of what eternity is. If it's eternal, it means that it's always the same and everlasting. It has no moving parts. If it has no moving parts, then
It's
there's
nothing
no,
and everything. Right.
yeah, well, it's like the source, right? So moving parts implies structure. As soon as you look at anything that has structure, it's a number. Depends how you want to quantify it. You look at anything. It could be anything. Well, mathematics is primarily concerned with ideas. Physics is concerned with material objects. And then everything draws from there: biology, architecture, engineering. But mathematics goes into the perfect archetypal things. Like you're like, well, if I'm here in some space and here, I could be any dimensional space. It could be two-dimensional space. But does it, like, we make up things that like don't even necessarily exist, right? There's no such thing really as two-dimensional space in physical manifestation, right? So a mathematician isn't interested in physical manifestation as much. They're like, yeah, we know that math basically models physical manifestation in ways that physicists have yet to find out, right? They're like, oh, strings in 11 dimensions. And they start realizing that black holes are doing this math that everybody thought was unapplicable to anything, right? But it's this really strange math that you wouldn't think, but literally Einstein needed this math to show how the universe worked. Before Einstein, they had math of curved three-dimensional space. It seemed like, why would you even do that? Right? A mathematician says, because it's freaking cool, right? It's mathematician gets why. We're like, we want to find structures in this hypothetical curved three-dimensional space. One day a physicist comes along named Einstein and he says, I need that. Can I borrow that, please? And it's also not complete enough for what I'm trying to do. And so they had to work on it and make it more robust to define Freudian slip, define space-time and warped space-time under the influence of gravity and the way light moves through space-time. Required this esoteric mathematics that didn't seem applicable. So point is, mathematicians are interested in these abstract ideas, these potentialities. So we look at space or numbers or space, any possibility of here than there, or this long versus this long, or this area versus this area, this curvature versus that curvature. And we try to quantify it. But it's very subjective, actually. How do you quantify something? Well, how do you quantify it? How does he quantify something? How does she quantify something, right? A lot of these things aren't necessarily the only way to do it, right? I mean, sometimes there's one way and we can all say, well, that's a great way, or that's the primary way or something like that, but perhaps there's another way, right? So I'd like you to step into the paradigm that anything is quantifiable, and quantifiable means we can assign a number to it, like the number 7 or 8, right? How can we make a thing like a surface? Like, what if I drew an interesting surface like this, like, you know, in three-dimensional space, and I was like, quantify that. Well, you'd say, well, it's more curved than that surface. It's more curved than a plane. It's less curved than that surface. That's like really pointy, right? But I'd say, okay, well, quantify it better than that. Give me a number, right? Not more or less, right? If there's more or less, perhaps you can give it a number. So how could you come up with a number? So mathematicians like Carl Friedrich Gauss literally came up with something called Gaussian curvature. He said, well, I could measure the curvature of that point. That's actually really complicated to do. And he said, I can do it in any dimension, like fifth dimensional surface inside 6 dimensions. I could tell you the curvature of that point, right? So it's like really interesting things we can do. So we're looking at quantifying things. And one of the primary thing I'm sharing with you here is relative size. That's what it is. It's relative size. What does it mean to be relative size? It means if Joe is 1 tall, then Sam is 2 tall. And then we'll just say Sam is 2 and Joe's 1. And you'd say, well, 2 what? I don't know. It's not inches, it's not feet, it's not any of those things. It's relative to Sam and Joe are relative to each other. It's a relativity. You see, the thing about the universe is everything is relative to each other. Mathematics is relatively, it's all relative. Physics is all relative. We say gravity produces a force, and you know, this rocket produces a force. And we define everything in terms of a unit of force. We call it a Newton. But that's a relative one. This guy became Newton. Measurement of force. It's all relative. Everything is relative. So when I say, okay, I'm going to draw 2 lines, this line, let's do it this way, this line and this line, could you apply a number to this? Well, you might say, well, maybe, I guess I could tell you how many times bigger this one is than this one, right?
Yeah.
That would maybe be a number. So I'd be like, okay, 1, 2, 3. Let's call it 3. So you say, okay, this equals 3 and this equals 1. But only relative to each other. If you did a tiny one over here, you'd say, okay, maybe this one equals 7 and this equals 21 now, right? Oh, wait a second. I said 1 versus 3 and 7 versus 21. And I said basically those are the same thing. So the essential thing that I'm representing here is if I change the unit from this guy to this guy or back or any size, the relative size of this to this will always be a multiple, a number. It's like how much bigger, how many times of this is this? So it's 3. 21 is 3 bigger than 7, even if we use a small unit, or 3 is 3 bigger than 1 if we use a big unit. That's called a ratio.
Yeah. Okay. Yeah,
So
I understand this relativity.
wonderful, wonderful. You see, we need to like deepen, when you learn it in school, you're like, you kind of learn what, like, what do I do, teacher? I'll do this, 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 and this, and then I'll give you a star, right? You don't really learn. And then some people actually think about it a little bit more, and they tend to go down the path of mathematics and they're like, learn for themselves somehow. They may struggle, or maybe they don't think about it and get a good A and still go down that path, right? I'm somebody who thought about it deeply. I really think about this. I like to get it, and I like to share what I get. That's kind of fun. I get a kick out of that. So okay, so if I draw 2 lines, could you associate a number with those 2 lines?
Yes.
What would you guess for this one?
Well, we would say 1 and 2.
Okay, so that's 2 numbers. Could we associate one number?
3 or 1.5.
Well, if you said
What?
this is, so what I'm suggesting is that you said 1 and 2. I would see this as 2. Because the relationship between these guys is 2.
Oh.
This is
Okay, yeah, I see it. I see it. Okay, yeah.
you
Yeah, I
see
do.
that? Isn't it interesting? I've given you 2 lengths and I asked you for one
I
number.
gave you everything but the answer.
That's okay. I'm
Because my brain was like, all right, well, the second one's twice as big as the first one, so you need 2 of the first one. So there's 3 of them there. And
yeah.
there's 2 pieces, but it's 1.5 piece, so it's 1.5. Then you're like 2.
Well, no,
There's just 2 things there. Okay, got it. Relatively, one's twice as big as the other one, and there's 2 of them. So I mean, maybe 2 is more logical.
but what if I told you, well, no, this is 100 long and this is 50 long? Would you change this number?
Um, not necessarily. No. Uh, there's still 2 pieces, and there's still 2 times
what's the relativity?
2.
It still has a relativity too. What if I said, well, okay, well, this is 1,000 now and this is 500. What's the
Okay,
relativity?
same. That's proportionately or scaling it the same.
Exactly. So the relativity is 2. Now you're gonna get something
2
that,
to 1, or yeah.
so when I say 2 divided by 1 is the same thing as 100 divided by 50 is the same thing as 1,000 divided by 500. And all of those equal 2. That's what I'm saying.
Ah, bing, bing. Yes. Yes.
Isn't that cool?
Yes. Okay. Yeah.
No, this is great. This is a fun little exercise. I mean, I'm teaching this to you in a way that I'm like just stepping out of the box and really saying what this means. And a lot of people who've been doing math their whole life don't even necessarily think about this. I mean, I don't usually think wait a second. These two numbers are actually one number in a relative, one number that is a relative quantification. It's
Yeah, you know what? That helps, dude. Seeing all three of those together helps me because with the 2/1, I'm thinking, oh, okay, 2 gets divided in the 1.
yeah, but you see, when you
And
said
then,
two gets divided, what does
yeah,
that verb mean?
yeah,
That verb doesn't actually have a lot of meaning for you.
yeah, it's just splitting it up, and then there's a 1, and so that's confusing me. But then I see the 50, and I'm like, okay, well, then that's just 2 pieces there. And I'm like, why did I not see 2 pieces from the 2 on the 1, but I see 2 pieces of the 100 over the 50?
Mhm.
And it's like the more the numbers, the more I'm like, oh, well, 1,000 cut in half is 5,000. 5,000. I mean, it's supposed to be 10,000
Oh,
there.
oh, sorry. Thank you.
Yeah. But I read it as 10,000.
Yeah, I meant to do what we did on the last diagram, which was
Yeah,
1,000
yeah.
over 10.
So then I was like, well, 1,000, with the 500, there's 2 500s and 1,000. There's
Exactly.
2
So
50s and 100. There's 2 1s and a 2.
so
Ah,
I've got two lengths, and you're quantifying both lengths together as a relativity equal to 2.
so there's 2 1s in that second one. So it's 2. Okay.
Well, actually, it's not two ones, it's two threes. And I'm messing with you. I'm messing with you because
It's two tens.
it's two tens, it's two
It's
anything.
whatever it is. It's relative. It's just relativity. Got it.
Relative, that's my point. Yeah, exactly. It's
It's
relative.
not a number. Ah.
The number we're measuring is the relativity. We're not measuring the length.
The number is just there for speaking the language of human, but it's not really a number. But we're giving it a number. It's relative. Got it.
Yeah. Well, we could give this numbers, and that means we're doing the division of 6 divided by 3 equals 2. What I'm saying is a length of 3 and a length of 6 has a relativity of 2.
Yep.
Okay, so now every time you see a division, you have a semantic reference point through which that thing makes personal sense to you experientially, and it becomes personal to you. It means that this is a part of your life experience in this realm of duality. Duality meaning quantifiability, measurability. In fact, doesn't Maya actually mean measurable? You know, in Sanskrit, the word for illusion is Maya, and I think it actually means measurable. Or there's a word very close to it. Literally, the word for illusion is measurable. Isn't that interesting?
I didn't know that.
I have to find exactly which word it is. I think it might be Maya. Um, so, all right. So now the interesting thing is, I gave you a 1 and a 2, a relativity of 2. I gave you a 1 and a 3, a relativity of 3. I could give you 1 in any number, right? But I could also give you 1 and 1.5, right? The relativity is like one's not more than 2 bigger. It's a fraction bigger, right? Checking out.
No, I am a little bit tired, but I'm not checking out.
So this is 1.5. That's the relativity. And
Okay, I see it. Yeah, I see it. I see that.
so we can have a relativity that is between, like if you have a number line, here's 0, 0, 1, 2, 3, 4, 5, right? We did 0, we did 2 and 3, right? Well, we could also do, we did this one and this one, but we could also do this one. We can do it in the middle. It doesn't have to be multiple of the other. You can't be like, every person is the same height, and some people are twice as tall, and some people are 3 times as tall. No, that's not how it works, right?
Right. Okay. Yeah. Huh, it's interesting how it's so easy for me to grasp it when I'm seeing it as pictures versus when I'm seeing it trying to comprehend the numbers, just in general.
I'm
But
the reason
observe that.
it's not easy for any of this. We're doing a very special thing here. The reason you're grasping it is because I'm describing it and you're listening with sincerity. And I'm describing it in such a way that it can meet your real life experience. I'm not leaving anything unconsidered or unspoken on. I mean, if you ask somebody, describe to me what this means. And why does that equal one number? I'm not sure they would even exactly know why, right? They know what to do, but what I just said here is two numbers. This is actually quite profound. I mean, even for me right now, I'm like, whoa, that's actually really cool. Two numbers are one number in a relativity. A number 2 and a number 7 are actually one number in a relativity.
Ooh, I like that. I like that. Two numbers as one number in relativity. I'm gonna write that down.
Like if you just get that today, speaking of bang for your buck, like you said last time, that's that's worth $500. It's very valuable. If you just got that, and really got it for the rest of your life, you'll walk around with that.
That was the golden nugget right now and all of this last 19 minutes here.
Yep.
Yeah, that two numbers is one number in relativity. That made the numbers click for me. At least I think. I feel like something went click.
Well, are you understanding that things can be measured as relativities? And when I say
Yes.
things, notice my language
Well, I
insinuates.
was trying to get the word divide out of my head, and I was trying to figure out how to see that as not division. And then once you said two numbers is one number in relativity, and then I see that division symbol, it just changed it.
We can quantify the relationship of things where we use an S to denote plurality, right? Things, multiple things, can be quantified by one number when you look at the relative nature to them. And in fact, everything is quantified as a relativity. What is it?
That actually is great. Yes, that makes me think of music.
Well, think about this. This is really interesting. Everything is quantified as a relativity. So if I said, you were like, well, what are you talking about, Adam? I see this thing outside. It's 3 meters. That's not a relativity. Or is it? It is. Because as soon as I say 3, you say 3 of what? And you say 3 of this special unit called a meter that we've defined.
It's relative in meter. Got it.
Somebody decided a meter was 1. Somebody decided an inch was 1, a foot was 1, a decibel was 1. A degree Celsius was 1. A degree Fahrenheit was 1. In physics, everything is actually a relativity. This is a major existential awakening if you really grasp it. Look around your room for a second. And notice that what makes things what they are is their relativity. In fact, you might even say there are no such thing as things. There are no things.
It's kind of a little bit of a head trip thinking that right now.
You're
Yeah,
like, well,
everything is just
you're like, well, this object here is a
size to something else and relative shape to another, relative space from one another.
so you're like, well, what's big? What's small? Well, I mean, there's no such thing as big and small. It's all relative. One's bigger, one's smaller. One's smaller, one's bigger. Two objects are relatively sized. But are there really objects or is there just stuff? What makes one object an object to the exclusion of some other object? Well, definition. You might say, well, that thing sitting there is also touching the air. Isn't it a part of the air? Isn't it a part of the atmosphere? you impose upon reality something that doesn't actually exist inherent to reality, which is that that thing exists and that thing exists, but that's only because of language. Here's my mouse, here's my microphone. I've defined these things because they have utilitarian value to me. So I say, there's my mouse, there's my microphone. But there's just stuff. There's plastic and wood and air, and it's all growing out of the soil of the earth. We're like clay statues that are built out of the soil and returned to it and rebuilt. We're just the earth taking complex formations on its biospherical shape.
Yeah, it's like nothing's really separate. I get that because it's kind of like plants, you need to eat them to survive. So it's technically they're an extension of our physical being because without them we die.
But
So
if you just
technically,
look, if you just look at the contents of space, the contents of space, or even space itself, is only, we only experience the proximity of the stuff the way we do. I mean, if you look out at Jupiter and you see there's this really great film, Interstellar. I'm sure you've watched it. In Interstellar, you see this little tiny spaceship floating in interplanetary space. And you get the sense that that spaceship is so far. I mean, can you imagine being in the middle Pacific Ocean? That's very far from anything, right? But can you imagine being 1,000 Earths away from anything else? And there's no water even, it's just vacuum. That's crazy. And you get the sense of the vastness or the sort of incomprehensibility of things. Things are as they are. There's no one and two. That's all relativities. Also in Lucy, towards the end of the film, Lucy, she talks about that. She says one and two, and maybe we should watch that. She says one and two, those aren't actual, those are just human constructs. So what I'm saying is that humanity, to make sense of things, has imposed upon it the idea of separate objects called things that we use and interface with. And those separate objects have relative sizes. And one of the things that we've introduced is the meter, the foot, the inch, the degree Celsius, the degree Fahrenheit, all these different ways to measure everything according to some unit, some scientifically recognized unit that we all agree upon. It's only a unit because we agree upon it, through which we can measure everything else.
yeah.
So if they say, how old
That
are you?
that I that I can grasp. Yes.
Nice. So when we're talking about phi, it's essential that you grasp this because phi, by its very nature, is a relativity.
Okay. Yes.
That's why the golden ratio exists small and big. You could have a small golden ratio in your credit card, or you can have a big one in your building.
So phi really isn't a number more than it's just the relativity between two things.
It's a relativity between two things. Exactly. That's the point. And there have to be two things.
Because it could be feet, inches, meters, doesn't matter. It's more of that relativity, which we call 3.618, but it's really not that. It's just the space in relativity between each other.
1 point, not 3.61.
Yeah, sorry. I was sorry.
Yeah,
Yes.
I feel like
But but what I'm saying though.
yeah. Well, 1.618 is a relativity to one.
But one could be anything. It could be 10, it could be 100, it could be
Yeah,
1,000.
we have two lines. One is 1 and one is 1.618. Well, here's another thing that we haven't. All numbers are actually relativities to the super unit called one. One is a super unit. It's more archetypal and transcendental than a meter or an inch or a decibel or a degree, because it is the mathematical relativity. Mathematics itself is relativity. Numbers are multiplicities.
Ah,
multiples of,
okay, okay. This is starting to make some. Not, I'm starting to deluge the numbers a little bit and see them more as reference points.
yeah, they're related to each other. So if I say 3, you think 3 units of 1. 3 literally means 1 plus 1 plus 1. If we were teaching a 3-year-old, we would say 1 plus 1 plus 1 equals 3.
Yep. Okay.
We wouldn't necessarily say 1 puppy plus another puppy plus
But
another.
3 is also 1.
Well, listen to what I'm saying. We wouldn't say a puppy plus a puppy plus a puppy equals a basket of 3 puppies, right? Right? Like that is talking about puppies, right? Or a meter plus a meter plus a meter is 3 meters. We're just talking about something that is unqualified. This is what makes math. This is why I love math. This is why it's so magical to me. It's so pure. It's purer than water, or even it's like ether. It's so unqualified. 1 plus 1 plus 1 equals 3. No matter what the 1 is. The 1 is just 1. It's the transcendental unit. By the way, this is such an ontological mathematics lesson you're having here.
Yeah, and then I'm like thinking there's like a paradox for me happening too, or 3 could just be 1 as well, because 3 inches is of 1 unit.
Ah, so you're saying, okay, Adam, so if 1 is 1, then 3 can also be 1,
Yeah.
which would make 9 3.
Yeah.
And so in mathematics, we always go back to this relativity with 1, but the relativity of 3 to 1 is the same thing as 9 to 3.
Right. Or if I'm looking at a 3-inch pillar, and that's just 1 pillar.
Exactly, but as soon as you say 3 inches, you could redefine an inch as 3 times bigger, and then you would say cinch.
Yeah.
You got it's not 9 inches anymore, now it's 3 cinches, right?
Yeah.
We just changed the name, right? And cinch
Okay,
is,
so now my brain I feel a little bit relaxed now.
so how do we measure if this is 1 and this is 1.618, right? First of all, what does 1.618 even mean? What are these numbers? Now let me just ask some ridiculous questions here. Like, if you were an alien looking at our language, you'd say, well, I thought you said it wasn't bigger than 2. Why is there a 6 there? And an 8 as well. And I thought you said there's only 2 objects. Why do you put 4 numbers? Right? So I'd start saying things like that, right?
Well, the decimal, you know,
Yeah, what's a decimal is basically my question. What is a decimal?
it is
1.
it is the quantifiable amount that's leading up to the wholeness.
What does 1.6 mean?
Well, it's
Like, what is
1
it
and
actually?
6/10
Oh,
if we're
okay,
using
that's actually really good. 1 and 6/10. But
if
what
we're
is
if we're using 10 base.
base 10? Yeah. So what is 6/10 though? Because we're
10
drawing this funny line again.
is 6 degrees to a whole 1.
So it's a relativity again?
Yes.
Okay, so it's the unit plus some relativity?
Yes.
Okay, so then we're saying, okay, so you're saying 6 to 10. So if I drew something that was 6 tall.
And 10 is really just 1. It's the 1 is
Ah, that was really intelligent what you just said. The 10 is actually the 1. Exactly. That's what we've done. We've taken a 6 tall and a 10 tall, and we've kind of returned the 10 into a 1. And now we call that 0.6.
yeah. Yeah.
Something actually this fundamental in math it gets a little confusing when you really break it down.
And then, so, but that actually it felt good when I said all that. I really understood what I was
You
saying.
really got that. You said the 10 is the one in the relativity, making the 6 actually 0.6, right?
Yeah, yeah. Uh-huh.
Beautiful. And then if you did it again, and he said, okay, 6.1.61, that next one is a 1 to a 10 again, or you might say it's the next layer down, right? So it's 1.6, and then we've got another 1.
I know this is where it's getting a
Well,
little.
just think of it relative to the 6. It's 1/10 as big again. I mean, you could say you could
Okay, okay. Hold on. Let me sit with that for a second. So, but if I'm thinking of it as hundredths,
yeah, you could do two ways. You could think of it as we're kind of doing this, but we're doing it here again, right? So it's kind of like we just went to the 10 again. Or
so
you could or you could think of it as this. You could think of it as 1 and then also 0.6 and then 0.01. If we add these together, that's 1.61. This is a
ooh,
tiny to a tall. We made the 100 a 1, so that's actually just very small. Maybe that's a nicer way to do it, actually.
yeah, that's pretty cool. Okay.
Okay, so then if we did it again, we have 1, we have 0.6, we have 0.01, and we have 0.008. And you're like, okay,
That's a thousandth, or even if just not even thinking of it that way, it's a 1/10 of one.
it's 8 out of 1,000, where we made the 1,000 a 1, and then we shrunk it.
That's so. How do you even see that difference unless you go like for thousands of feet? Then that will start to kind of,
Oh, this is very small.
yeah. You would have to go literally 1,000 feet to even experience that difference or something like that, right?
Well, because it's 8, which is almost 10, you see, this one and this one are almost the same size. This is 80% as big as this.
Yeah.
Another way you could look at this, watch this. This might help too. You can think of this as 600 out of 1,000, 10 out of 1,000, and 8 out of 1,000. And you could think of it as 1,000 out of 1,000 on the top. So if this is 1,000, and then we went 600, and then we went 10, and then we went 8, we'd be approaching the golden ratio.
That's real small,
Well,
but
you know how many digits, they know the golden ratio to? I mean, it's like trillions.
yeah, I actually have a book that has the whole number, and it's like 3 pages long.
Well, and remember, you can never get the whole number with this number system because you would always be a little bit short because you can always add another
Yeah,
digit.
but then you can only see so much space and time, so you'd have to be like, a microatomic ant to get to that exact point.
And as a mathematician, we like to define things directly. So I would say it's this. It's the number that multiplied by itself equals 5/4 plus the number 1/2. And we don't need any more decimal places. We don't need any decimal places, in fact. That is the number right there.
5/4, because 5/4 is
No, I haven't explained to you why. This is actually quite
okay.
tricky
Because
to
I
explain.
know that 5 relative to 4 is 1 whole plus 125% of 4. So
125% plus 50%
is
equals
175, is 100, is 100. That's a
no,
little more than 618, to be honest.
no, it's exactly 1.618. Because what number multiplied by itself equals 1.25? Well, watch this. 1.118. If you grab your calculator and type in 1.118 times 1.118, you'll be amazed that Adam happened to somehow know that that equals 1.25.
It says 1.249924.
Huh? And if I added more decimal places, there'd be more nines. And now add 0.5 to 1.118. Or I mean, sorry, yeah, to 1.118.
plus 0.5, you say?
Uh-huh.
1.74.
No, 1.118 plus 0.5.
Oh, 1.118. Oh, okay, yeah. But if it's, oh, right. Oh, because 5 over 4. Oh, because 5 over 4 is 1.25. And then, so that would be the square root of 5 over 4. And then,
Which
so,
is a little smaller, right?
so 5 over 4 is just 1 point. Wait, what?
The square root of 5
For
over
a
4.
second. Yeah, the square root of 5 over 4 is 1.118.
Uh-huh. Dot, dot, dot.
So a number times itself equals 5.4.
Yeah.
Wait, 1
Some,
point.
some number times itself equals 5/4. What number is it?
Oh.
So I'm gonna do something else that's gonna be a
So,
little
but then why is it 1.118 plus 0.5, but you had a 1.25 plus 0.5?
no, but I don't, because it's inside the square root.
Oh, it's a square root of 1.12. Oh, okay. That's what I was missing.
Yeah, you thought it was 1.75 because you didn't realize that square root doesn't mean the value of that is point
So
one.
the square root of what, let me just, okay, the square root of 1.25 is 1.118. And then, so then I'm going to add that with plus half. Okay. All right, I'm writing this down. Plus equals. Squared equals. Okay. Point. All right. So then, can I take anything, do the square root of that thing, add it plus 5, half of that value?
So let's do a few. Okay, so a few properties of this. The square root of 1.25 plus 1/2 has some interesting properties. First of all, this equals 1.618, but 1 divided by 1.618 strangely equals 0.618. And that's not the case with most things. 1 divided by 1.5 does not equal 0.5. Definitely not. This is the only number that I know of that does that. Well, actually, let's see. Well, there's other numbers that do other strange things similar to that. So this is a property of phi, that 1 divided by phi equals phi minus 1. 1 divided by phi equals phi minus 1.
Square root. Okay. 1 divided by phi. Okay, yeah. Okay, I see what you're saying. The relativity of 1 and 1 is 618. Okay, yes, got that. Yep.
And the reason for that is if we drew this thing again, like we did in the beginning, and we said this is 1, and the whole thing is 1.618, then this is 0.618. Just see that has to be obvious, right? Because
Yes, because 1 plus 618 is 1.618.
Good. And we said that this is to this as this is to this. So 0.618 divided by 1, 0.618 divided by 1 is the same number as 1 divided by 1.618. right? This is to this as this is to this. We specified that we wanted that relativity, required that relativity when we were finding this number.
If I type in those 618 divided by 1, it just says 618. It doesn't add at 1.
If you type in 1 divided by 1.618, you'll
If
get,
I type in 0.618 divided by 1,
yep. That's the the trivial solution, right? Anything divided by 1 is itself.
yeah,
This is the interesting part, that equals this now.
yeah.
That's what makes it crazy. You should be very, if you're not getting it, if you're not,
No, it does. That is crazy because that's the only thing that will be exactly that, right? It's the relativity of the whole is the big.
well, try this with your calculator. 1 divided by 1.8.
A lot of 5s and with a 6 at the very end.
But it's definitely not 0.8, right?
Yeah.
What about 1 divided by 1.4?
Okay, yeah. So this is the only number that's going to be the exact same relative.
Now do this. 1 divided by 1.618.
One. Yeah, there was a forget what the number was, but the golden root. I was looking at it the other day.
No, this is the number that brings at the foundation of all those golden things. Golden spiral, I don't know what you mean by golden root, but this should be astonishing to you. 1 divided by 1.618 is 0.618.
Yeah.
And if you did this with a lot of numbers leading all the way up to 1.618, 1.4, 1.41, 1.42, 1.43, 1.44, you'd be like, wait a second, it's getting closer to the number itself. And then
So if I
right
did the square root of 1.618, that would be the golden root. What would that be? 1.618.
square root of it.
Yeah, the square root of that is 1.272.
1.272.
And if I divided that by 1, it's 1.272.
No, it's always whatever you divide by 1.
Okay. I did it backwards. Wait, let me go in reverse. 1 divided by 1.272.
But let's not focus on the golden.
0.786. Ah, okay, never mind.
No, there's nothing. That's if there's something there for us to discuss, it's more complicated. Let's stay focused.
Okay, I'm sorry. I thought that was gonna find something.
You're letting me down now, Soleil, because you're not being surprised by the fact this is the big punchline. The firework display just went off at the end.
Yeah, no, I got it. It's amazing. I get that. Yeah, the relative to each other, it's the equal frontwards and backwards.
Okay, and there's another one that's interesting. That so 1 divided by 0.618 all equals 1.618. That's the other way around.
Yeah, that's what I just did a second ago. It's 1 divided by itself.
No, but no, I now this is a 0, not a 1. I switched these two. See that? They're switched.
Yeah, exactly. Yep.
Okay, let me show you another one that's interesting. 1.618 times 1.618 is 2.618.
Holy shit, yeah. For some reason, my calculator is saying 6179, which is
The reason it's not going to be precise is because we didn't say all the numbers. There's many.
Okay. Gotcha.
Yeah, you want to write 10 numbers in, you can, but then it's going to take a long time.
Okay.
We know it'll be exact. So here's another one. 1.618 times 0.618 equals 1 minus 0.618.
Ah. So if I did +1, wait, what? So okay, I just did that. 6.618 multiplied by 0.618 equals,
0.382.
yes,
1 minus 0.382 is?
382 plus 1 is 1.382.
No, 1 minus 0.382.
1 minus 0.382. Oh, oh, ha, that's cool.
So this is all special because of phi.
Damn, that's really cool. Okay.
So let me write these out. 1 minus phi squared. Well, okay, it depends how you want to define phi. So let's call phi. Usually people say it's 1.618, but I kind of like to say it's 0.618. So 1 divided by phi squared minus phi squared equals phi. That's what I just showed you.
So how would I apply that on an object?
On an object. Well, wait a sec. I'm gonna show you all the different interesting things. 1 divided by phi squared equals 2 plus phi. There's like really some interesting things going on here. Like you see, you can have all these interesting equations from it. And 1 over phi equals 1 plus phi.
So if I did 10 divided by 1.6, 10 divided by 1.618 equals that 6.18.
Exactly. Yeah, because it's
Times
10 times
2 times 2 itself, 12.36, which 0.36 was 618 if I minused the
So
1.
there's a bunch of
And
phis. So when I watch this is how you can see it as an object.
divided by 2.
So check this out, Soleil. I can take like an arm and take it here and rotate it down to here. And we have this special rectangle. This is one golden rectangle. That
Yeah.
that dimension. We could also take this arm here and rotate it down here. And this is another golden rectangle.
Wow, that's badass.
So those are once my teacher said to me, and I didn't know what he was talking about. I said, the golden rectangle, and I said, no, not that one, the other one. And I was like, what do you mean the other one? And what he meant was what I just showed you. There's two different proportions. It can either be the small to the whole, the big to the whole, which is the same as the small to the big. So there's actually two there. Perhaps there's even a third.
And then, wow. And then so if I doubled, okay, so that smaller, the 6.18 part, if we were to make this skinny rectangle off of that one and then double them, what would happen then?
No, you're exploring, but it's not the same thing.
Okay.
If you doubled it, it would just be two of those golden rectangles. It's like asking what would double if you doubled the other one.
But it wouldn't be the same relativity anymore.
No, because yeah, it wouldn't have the same elegance because remember this is equal, if this is equal to 1, when we put this one down over here, that's actually 1 and 0.618. So it's actually small. This one's actually smaller than two of those.
Okay. Yeah. So there are some rules here.
Well, they're not, don't call them rules. Rules I feel is a bad word.
Okay.
Rules is a bad word because rules imply an authority that you have to follow and don't necessarily understand. Rather, you should be the creator and the architect here. I would say there's some elegance and there's some structure here that you can know. And these are rules only, okay, they are rules at this, they're rules because here's what I did. We came this far. There was a little moat that we couldn't jump across in the full hour. So I went to the end to give you some interesting insights, but we can bridge this gap so you can see it as self-evident. We just need to do that another day.
Okay.
Yeah, but I wanted to show you some of the properties of phi, which are also important to know. Their properties. The way that I just knew all those, do you realize I didn't even, it's not that I was memorizing. I mean, we're the kind of memorize some of them. I'd say some of them are familiar to me, but I was thinking about the properties of phi and writing them on the page.
Yeah.
That's what I was actually thinking about it. If I had forgotten the equation, I would have just thought about it and saw the equation. So,
Yeah, this is really cool. Thank you. Yeah. So, Monday.
yeah, can we do Tuesday? Because Monday I have another
Yeah.
session. That'll be a
Yeah,
little packed on that day.
that
Okay,
works. So
so
I'm gonna, and then maybe you would send this to me then.
yeah, I'll send you a YouTube link.
Okay.
And what did I want to tell you? So we've done three. How many have we done total? We did Monday, Tuesday, Thursday, Friday. So
This is lesson number,
3 of the package, right?
um, 1, 2, 3. Yeah, this is number 3 out of the package. Yeah.
So you have 6 left. Cool. Well, we're
Yeah.
gonna look how much you're gonna learn so much. We're only a third of the way. Oh, do you see how I did that?
Yeah.
3 and 6. 3 is 1/3 out of 9, even though 1/3 out of 9, even though the ratio is 3 to 2, 1 to 2, because it's 3 to 6, which is 1 plus 2 is 3, right? You see, there's all kinds of structure there.
Thank you.
You're welcome. Nice to see you.
Yeah. Have a great class. I'll see you soon.
Thank you. I don't have any more class. Oh, you mean today?
Yeah. Oh, yeah.
No class on Friday.
Oh, well, nice. Have a nice rest of your weekend.
Thank you. Thank you.
And your following class on Monday, and I'll see you Tuesday, same time.
You're not in LA, are you?
No, I'm Texas.
Oh, okay.
So I'm 2 hours ahead of you.
Because I've got a meditation. I want to send you a flyer that I'm doing a meditation party on Sunday.
Oh, nice.
So I would have loved for you to join if you know anybody that would want to come to a meditation party.
Sure. I might know. I know a few people that would definitely love to attend if they're available. I'll send them a message. Shoot me the
Cool.
link.
Cool. Thank you, Soleil.
All right, you
All
got
right,
it.
I'll see you later. Thank you.
Yeah.
Bye. Namaste.